Hi, everybody. Let's get started. Just one quick announcement, or a couple quick announcements before we get into today's material. You can see that I have most of the office hours posted. It's not quite ready to go yet. Office hours are not going to start until next week, but I just wanted to make you aware that they are becoming more and more available. I'll post a message on Piazza when office hours are all squared away and good to go. But if you want to start planning out your weeks and things like that, you can check out the office hours on the course website. Another thing to note is that on Tuesday of next week, if you take a look at the calendar, that's when our first homework assignment is going to go out. So it is very, 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 very much to your benefit to come to class that day and participate. In fact, I'm going to spend the whole day basically talking to you about the homework assignment, and then we're actually going to get started on the homework assignment in class. You can earn credit on the homework assignment by coming to class on Tuesday. So please, 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 please come to class on Tuesday. Very, very, very important day in terms of the homework assignment. I hope to see you all there. Are there any questions about scheduling or logistical stuff before we hop into today's material? All right, great. Yeah, question.
Do you need to have like Java set up?
Oh yeah, good question. So the homework assignments are all in Java. That is true, and that includes homework 1. Homework 1 is in Java. I'm going to give you some starter code on Tuesday. I'll show you how to set all that up on Tuesday. We'll go through the setup process for that. But if you don't already have a way of working on Java code, which is basically like an IDE, like Eclipse, if you've taken previous courses in Java, you've probably already got Eclipse on your computer. I would definitely recommend getting that set up between now and Tuesday. If you need help with that, let me know, or honestly, ask around. Eclipse is used all over the place on campus, so you'll be able to find somebody who can help you set that up pretty easily. But yes, it would be a good idea to have that set up before Tuesday. Any other questions? All right. So what we're talking about today is actually directly related to the homework assignment. We're going to talk about the physical layer. We talked about this a little bit on Tuesday, a couple days ago. Let's start off with just a little bit of a review from what we talked about on Tuesday. The data in a database is stored on the physical layer in a different way than how it's shown to the users. Remember that what the database users typically expect to see is something called a schema. That's when we saw the ER diagram with the tables and the relationships connecting the tables. So that schema looks a lot different from how the data is actually stored in a file on the computer. Why? Yeah.
Well, it's because the data is stored physically in such a way that makes it optimal for retrieving. It doesn't mean it's a way it's conducive to how the user can find it or even like query for it.
Yeah, you nailed it. So the data in a file is going to be stored in a binary format, 1s and 0s. We're going to be doing a lot of byte manipulation for homework 1. That's where we're at. We're at a very low level, dealing with files, dealing with I/O kinds of stuff. So users don't want to deal with binary. Users don't want to deal with bytes. Users want to see something that's more relevant to the task that they're trying to perform. So they want to see the more organized structure. They want to see the tables. And so then it's up to us as database designers to figure out that mapping, right? How do I take something that's in binary, that's in bytes, and convert that over into something that's more useful to the database users, into a schema, into a set of tables and columns. And vice versa, right? If somebody manipulates the tables, the rows, and the columns, I need to then map that back to the file, know where that information is going to go, what to do with that piece of data. So what we're going to do today is talk about this physical layer in a lot of detail. Oh, one more review question. Great review question. What kind of information is stored in a database system? I asked you, I think, almost this exact same question on Tuesday. There's an easy answer and then a less obvious answer. Yeah. Metadata, yeah. So that's the big answer I was looking for. Metadata. we keep metadata as well as the actual data. So what's metadata? What's an example of some metadata that we talked about? In the back.
Like what bits that certain bit positions mean with regard to, say, columns or fields.
Okay, yeah, so what structure does the data actually take, right? How many columns are there, right? What order do those columns appear in? What else? Yeah. Database description? Description of what exactly? I think you're correct. Can you be a little more specific? Descriptive information, like what? Like what kind of, what are we describing? Can we be more specific? Yeah.
Just like the relationship of all the data, the pattern of the data, and just like you can find there's specific pattern between the data can explain how the data is generated in the data structure.
So relationships, right? Relationships are also metadata. How does this data relate to this data? Yeah, in the back. It's information about data. That's right. Yeah, file size is a great one. How big is this file? How big is this piece of data? What are the data types? That's a classic form of metadata. I have this information. All right, is it a string? Is it an int? If I'm looking at this series of ones and zeros, right? How do I interpret that? How do I interpret those bytes? That's all metadata. That's actually, there's tons and tons and tons and tons of metadata that your database is storing for you. And so some very important questions. Should all of this data be stored in the same way? Am I going to treat metadata just like normal data? Is there any reason not to? There really isn't. If you take a look at a database, you'll see the data, of course, the tables with rows and columns. And if you want to go find the metadata, which you actually can, you can find it. I believe one of the studios has you do exactly that. You'll notice that the metadata is also stored in tables with rows and columns. So somewhere in the metadata for your database server is a table that all it does is basically store, here's the name of the table, here's the columns that appear in that table, and the data types for each of those columns. There is a table in the database that describes the other tables in the database. Right? There's another table that just says, there's a relationship between this table and this table. It just tracks that, right? These two columns from these two tables are linked up. This column is the primary key of this table. That's metadata. It's going to be stored in a table, just like any other information. This is all accessible to you when you look at a database. And it's managed for you as well. Except we're building a database from scratch. So now it's our job to manage that metadata, right? We now need to keep track of all that metadata in order to perform the tasks that a database is expected to perform. And so this last question doesn't have a simple, straightforward answer, but it's something that I think we're going to be talking about a lot as we go through today's material is, what's the criteria for data storage? There's some obvious concerns. We want it to be fast, but that's not the only criteria. What else are we concerned about? Yeah. I'm sorry?
The storage.
The storage, the space, the size. We care about size. And those two are often sort of at odds with each other, right? I can make things go a lot faster, but it's going to take more space. Or I can reduce the amount of space that something takes, but it might take me a little bit more time to perform actions on it. So that's a very common trade-off that we see in computer science, and it's true here as well. And so it's really up to us. Again, we're designing a database from scratch. We now can answer these questions in a way that makes sense for us, that appeals to us. Let's talk about data types real quick. I mentioned data types very briefly last Tuesday. I don't know if you had a chance to go through the Studio 1 between now and last class. But if you did, you definitely saw some various data types. We're familiar with data types from other languages, right? The concept of a data type is nothing new, but the data types that you see in a database are different from what you're used to in other languages. So while we have strings, for example, what is a string called in a database? Anybody know? Yeah. Varchar, yeah. That's not the only one, though. That's one kind of a string. Yeah. Taylor. Just text? Okay. So in some degree, it depends on the database implementation, right? For the version of, for the server that I had you set up for the studio, MySQL, there's actually at least 2, if not more, data types just representing strings. There's varchar, and then there's also just plain old regular char. Does anybody know the difference between the two? Does anybody know the difference? Yeah. You're right. I think there's a little bit more nuance to what you just said, but you're absolutely right. Varchar, as its name implies, allows you to store a variable set of characters, but a regular old char does too, right? The difference is that if I define my string length to be 10 with a varchar, but I only have 5 characters in my string, it's only going to use 5 slots. If I have a char data type, and I say there's going to be 10 characters, but I only give it 5 to store, it's going to add spaces on the end of that so that it is always 10 characters long every single time. There's a couple of interesting things. Yeah, did you have a question?
So, it's about the implementation. So if it's about how it's dynamic, the storage.
Yes. Yes, so think about that. There's a couple things to consider with that. One is, like in Java, we create a string. We don't have to say how long the string is going to be. Java just figures it out, right? Java doesn't care. We just say, oh, this thing's a string, and we give it a string, and it goes on its way. With a database, we can't do that anymore. We have to say, well, this column's going to have strings in it, but none of those strings are going to be larger than this number of characters. I have to provide a parameter to that type now. I have to say, what's the upper bound of this data type? And then, to get back to your point, varchar is a variable length string, whereas char is fixed length. So think about what that means in terms of storage. If I'm actually storing these on disk, right, in a file, how is that going to affect if I'm searching for records, for example? How's that going to change my approach? Why do we even, it kind of gets to this underlying question of why do we even bother doing 2 different ways of strings? Why not just pick one and use that for everything? Yeah. Yep. Right. Well, let's talk about that a little bit. You hit the nail on the head. We're already seeing that trade-off between size and performance, right? If I have a fixed length character and I'm searching through some records, I know I can just jump ahead X number of bytes every single time to get to the next value because all of them are the same size. If I'm using a variable length string, a varchar, I can't do that. I have to somehow figure out where the end of that string is. And there's different ways of going about that, but there has to be a little bit of extra going on there to figure out where the end of that string is. So variable length strings ultimately will save you space, hopefully, because they're not going to add that extra padding on the end, right? But when it comes to searching for those values, it makes life a little bit more difficult. Whereas fixed length characters, even though I'm sacrificing a little bit of space, then it does make searching for things a little bit easier because I know exactly the size of that particular value. And this example shows up, all over the place in SQL, really. There are other variable length data types if we're dealing with binary data, for example. It's the same kind of idea. For just a few values, it doesn't make a huge difference, but if you think of a large database with lots and lots and lots of data in it, that choice could have a very significant effect. Good. What other data types have you seen? We talked about strings. Yeah. Date. Date and then time, and then a lot of times you'll see them glued together. Date, time, all as one. So yes, dates are very important. Dates are actually under the hood. Dates are just numbers, just integers, really. What else? What else we got in terms of data types? Yeah, go ahead. Boolean. Actually, there is no explicit Boolean data type in MySQL, but you can replicate a Boolean data type by using a bit, a 1 or a 0. Gets you there. And so a bit is really just an example of a very, very small integer, like as small as an integer can possibly be. So we've got those integer data types as well. Ints exist, big ints exist, and then your floating point data types exist as well. Floats, and they're typically called floats in SQL. And honestly, we've covered most of the data types. There's not a ton. There's not a ton of data types available in SQL. There are more that we haven't gotten to, but those are the major players. Those are the major ones that you're going to see out there. The reason that I talk to you about this is because the data type has an effect on storage, right? We already talked about that with the strings, but even if we think about, so let's zoom out a little bit and look at a whole record, a whole row. If I want to know how this record, how this row is stored on disk, I have to understand the structure of that record. So the first question, I hope, is easy. What affects the size of a record? It's the data types of the columns that it contains. Are all records in the same table going to be the same size? What do you think? Yeah, in the back. Not necessarily. The answer is maybe, right? Maybe. You could pick data types to where that would be true, right? If I make them all ints, well, that's easy. Then every record is going to be the same size. If I start picking variable length things, then no, that won't be true. They're going to be variable length records. And this has a big impact on how a record is stored. Has a very big impact on how a record is stored. So if I have a variable length column in a record, it doesn't just make it more difficult to figure out where that column is, but it also makes it more difficult to figure out where the end of that record is, right? If my records are fixed length, then it's very easy for me to jump from one record to the next, to the next, to the next. If a record can vary in size, then it becomes more difficult, again, for me to figure out where one record starts and the other record begins. So there are two different ways of approaching storage. Well, actually, there's a lot more than two, but we can think of storing variable length records or storing fixed length records. And if we're, just some ideas, let's talk a little bit about how we can approach this problem of storing variable length fields and variable length records. Does anybody know or have an idea of how you might take care of this? If somebody asks you, maybe I will ask you to do this on the homework, who knows? If somebody asks you to store a variable length record, how would you solve this? Yeah.
Linked list.
A linked list. So remember, we're talking about zeros and ones, right? So I want to know, how are you going to modify a series of binary values to indicate where one field or record stops and the other one begins? Termination, there we go. That's one classic example, right? I have a variable length string, and this could maybe go up to 20 characters, I don't know. But if this is the end of my string, I'll put a terminating character at the end of it. Done. That's not the only way. There's another way. Did you have a question or a suggestion? So tracking offsets. So like where in the file does this record begin, right? Is that kind of the gist of what you're getting at? Sure. That's another possible way of going about it. But let's talk about the difference between those two. Here, this character probably takes up a byte, right? So 1 byte for every variable length field. If I'm storing offsets for every record, that's probably what, an int? Or maybe we could get away with a small int, right? So we're talking about more bytes. Again, more space, but perhaps at the value of making it easier to figure out where things are, right? It's another trade-off. But yes, that is another way of approaching this particular problem. Or another way of approaching this particular problem, and actually one that's kind of similar to what we're going to see on the homework is, let's put the number of characters right out front. There's 5 characters in this string, so count 1, 2, 3, 4, 5, and then stop. Or if you don't care what the string is, then just go 5 bytes ahead, and you're at the next value, right? All 3 of those options are perfectly viable. This is pretty close to what we're going to see on the homework assignment, if for no other reason than it's simple. It's pretty straightforward. Are there any questions so far? Yes?
What did that make for very poor retrieval time?
Very poor retrieval time. How so?
Because if you want to find like the 500th entry, you have to count like the first 500 entries before you get to that.
Count the first 500. I'm not sure I understand.
So like if I have like 20 hellos, right, then I would have to look, oh, this one has 5 characters and this gives the next one.
Oh, sure. Well, so it depends, right? I guess I was a little bit misleading in how I specified this situation. The solutions that we provided aren't necessarily independent of one another. We can combine them if we want to. So maybe I've got a number of characters in front of every string, but I still have a terminator for the entire record. So at the end of the record, I still have a terminating character, and then that makes it easier for me to figure out when one record starts and the next one begins, right? So you can combine them together, so something like that. Or I could still use offsets if I wanted to in conjunction with any of these. Again, it's more overhead, but hopefully at the benefit of increased performance. Yeah. Yeah. Yes, this is purely how are we storing this data on disk. So somebody using the database is not going to see this 5, right? They're never going to know that it's there. Well, I'm going to have to read it in memory at least once when I pull the data off of the file, right? But then by the time it makes it to the user, any information like that has already been stripped away. So at some point during the query execution, right, I'm chopping off that extraneous stuff. Does that make sense? I feel like maybe I'm not answering your question. Oh, okay. Well, that's a different question entirely that I do want to address is memory considerations. I tell you what, let's put a pin in this for like 2 more slides and then see if I answer your question. Yeah. I like where you're going with it, though. Any other questions? Great questions, by the way. Keep them coming. Any other questions so far? Yes?
So that's why sometimes some like websites, when you use like a username or password, they don't allow you to use like some special characters. Maybe that they are using them in like.
I kind of doubt it. I mean, it could be. It could be that that's why they don't allow you to use certain characters. I chose a $sign here, but that's not necessarily what you would use in an actual implementation. In an actual implementation, you might use a byte that does not have an ASCII value associated with it, like 255 or something, something that you wouldn't expect to appear in a string. But $sign was just an example. Yeah. Any other questions? before we move on? Okay. So I've got a bunch of records. They're in a file, right? All these records are in a file. What kinds of operations do I expect to be performed on these files? What kinds of things am I going to need to do with these files? Yes?
Read, insert, delete.
There you go. You nailed it. Read, insert, and delete. I got to be able to get information out. I got to be able to put new information in. And I got to be able to remove information, clear out space. Those are the big three. Now there's other stuff that can make our lives easier, but in general, that's what we're interested in doing. Insertion, deletion, and retrieval. And so this actually can also have an effect on the way our data is stored. Or maybe it's better to think about this in the other way. The way we store our data has a big effect on how those operations are performed, right? Has a huge effect on how we're performing those operations. I mentioned in this class that we're going to use something called a heap file to store our data. It's a very simple, very straightforward mechanism for storing data. One of the ways that a heap file really simplifies the process is with insertion. Does anybody remember what we talked about in terms of inserting records into a heap file? Yeah.
Just get stuck at the end.
Just tack them on the end. It's as easy as that, right? Very, 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 very simple. I'm making some sacrifices by doing that, though. What's the downside of that approach? Yeah.
When any record in the middle was deleted, I couldn't use the same space.
Yeah, there's going to be a lot of holes, right? Eventually, I'll remove tuples, and I'm still tacking new ones on the end, so there's going to be a lot of gaps in my data. There's a couple ways we can solve that problem. One way is, okay, let's just periodically go through and, get rid of that fragmentation, condense everything down. It's kind of an expensive process, especially if your table's very big, but the results would be noteworthy. And so that's one way of going about it. Another way of going about it would be to incorporate what I introduced in class on Tuesday, which is a header that tracks, all right, is this position occupied or not? And so now if I have a header that's telling me whether slots in a file are occupied or not, I no longer have to insert things at the end. I can just go find the first available slot and put it there. But there's that assumes something, right? What's the big assumption that we're making if I'm going to use a header in that fashion? Yeah. Records are fixed in size. If I have variable length records, using a bit is not going to work. Question?
So is the exercise of having this header correctly allocated storage pretty similar to the exercise of memory management, writing like
Sure. Yeah, sure. Very similar. I mean, think about how memory is structured on a computer. It's also in a heap, right? It's not a coincidence that it's called a heap file. Not a coincidence at all. They're not exactly the same, but there's definitely some similarities between the two. So yeah, if we assume we have fixed length files, I can use a single bit for each area in my file and just say this slot's occupied or it's not. If I have variable length files, how does that change? Yeah.
Can they be bits that go to a pointer to where the data is?
Bits that go to a pointer, or actually just put the pointer itself in the header, right? It's an offset maybe. But that becomes a little bit difficult, right? Especially if I ask you how many records fit in a file. If I ask you how many records fit in a file, and the records are all the same size, there's some arithmetic there that you could compute and figure that out, right? But if they're not all the same size, I say, how many records are going to fit in there? You're going to say, well, I don't know. I have no idea. So you might be telling yourself, oh, yeah, so that means that fixed length records make life really easy. And that's kind of true in some ways, but we end up paying for it in other ways, namely space. Namely space. We are going to use fixed length records in this class, though, for our purposes, because it is a more straightforward implementation. And so let's talk about heap files. This is perhaps the simplest physical format that you're going to find on any database anywhere that's in existence. It doesn't get much simpler than this. There are other ways. In fact, I think if you looked at a professional database like MySQL, they probably are not using heap files, would be my very, very educated guess. But we're going to use heap files because it's simple, because it's straightforward. The records are unordered, very much unordered. So let's talk about the performance of these heap files. Insertion. We already talked about how to perform insertions. We actually talked about it in a couple different ways. What's the efficiency of insertion? Kind of depends on which way we pick, right? If I just tack everything on the end, that's easy. What's the efficiency? Constant, right? Doesn't get much simpler than that. If I use the header and I try to conserve my space, use my space appropriately, what does the efficiency become then? Yeah. O of n, where n is number of records. Yep. The very worst case, I'm going to have to add that record at the end after going through all of the other ones. But really, what am I going through? I'm going through the header, right? I'm not actually going through the records themselves. I'm iterating through the header, finding an open slot, going to that position, putting the record in that space, right? So if I want to find a record, what do I do? What's the process look like? Let's assume that we have the header. We're using the header in conjunction with this operation. There's a record that I want to find. How do I do that? Where am I going to start? Yeah. Linear search. So the efficiency then would be n as well, based on the number of records, right? But it can actually be faster than that on average, especially if the file's not full. Again, because we have the header. So I can look at the header and use that to help me. If the slot's unoccupied, I'm just going to skip it and go to the next one. Why bother searching something that's not there, right? So it can help speed that process up. Yeah? You can have the length of the string as a factor. Is that what you're getting at? I think that's true. I think that the dominant factor is still going to be the number of records, though, is it not? Of the two that we're talking about? I suppose it depends on, so search is, maybe using the word search here is even a little bit broad. Do I know, do I have to search every string within a record, or do I just have to search one of this? Am I just looking for a particular string in a particular column, right? That makes a difference. So, you know, search here is a very broad term. In general, the most general case, I think it's going to be based on the number of records. And then let's talk about deletion. How does that work? How would you delete a record? This is a little bit tricky, actually. Yeah. Mark the bit in the header. Yeah, just turn it off, right? But I have to find it first. And this is where, again, we have a couple ways of approaching this, right? I could say, go find a record that has this value in it and delete it. In which case, I have to do a search first. I have to. But there's another way that we could consider deletion. Maybe I know exactly what record I want to delete, right? I have a very specific record in mind. So I can just go directly to where that record is. Maybe the record knows where it lives. That would be useful, wouldn't it, if the record knew where it lived? So then I can just go directly to that particular spot and update the header to reflect that it's no longer there. I don't actually have to remove the data. That doesn't make a difference. Just switching the header is enough. And then how do I perform a modification? Maybe I don't want to remove data, but I want to make a change. How does that work? Yeah. Yeah, so there's two ways we got to consider, especially if we're using variable length records. If it'll fit in the same space, then I can do the modification directly. But if it can't, then I have to move it, right? I have to move the whole record somehow. So that means I have to delete it and then basically insert the new one. In fact, just to keep things simple, that's usually what we always do. We just delete, especially because we're using fixed length records. We're just going to delete and insert. The insertion time, especially if you're using append to the end of the file, is constant anyway, so it's not a huge performance loss to do it that way. You could make arguments about modifying in place, but typically, or at least for our purposes, we're going to treat modifications as a deletion followed by an insertion. Any questions? Any questions at all? All right. Here we go. This is what I thought might answer your question in the back. Is it faster to manipulate data on disk or in memory? This is hopefully an easy question. Memory is way faster than doing things on disk. So we have to read in our physical data to memory when we want to make changes to it. But consider that databases are very large, right? Databases can get to be huge. And I haven't explained we haven't gone through the entire file structure yet, but typically there's going to be one file per table, or it's actually possible to have multiple files per table. But a common representation is one file on disk per table in your database. So as your table gets bigger and bigger and bigger and bigger and bigger, your file also is getting bigger and bigger and bigger and bigger and bigger. So think about what that means. Eventually, that file is going to get so big, it's not even going to fit in memory anymore. And now I've got a problem. My performance is going to start to tank. Any ideas on how we can solve this problem? Yeah.
Can we just read by chunk?
Yeah, exactly. We're not going to read in the whole file at a time. We're going to break the file into pieces. We'll read in one piece at a time. So those are going to be called pages. We have a heap file that is comprised of many heap pages. And a page is what we're going to read in as a unit from the heap file. That's how we're going to solve this memory problem. So even if I have to go through the entire table, which is going to happen sometimes, right? I'm going to have to scan through every single record in a table. I'll read in the first page, scan through all the records, and then get rid of that page. Once I'm done with it, read in the next page. Actually, if we want to be a little bit more accurate, I can have more than one page in memory at a time, especially if I keep my pages relatively small, and it's beneficial for me to be able to do that. So really, there's just a limit on how many pages I can have at once, depending on the architecture of the system that you're working with. So when I've been talking about a header and records, what I was actually talking about was not the heap file, but the heap page. A file is going to have many, many, many heap pages. Each heap page is going to have a header. And then after the header is going to be the records. The records are stored as tuples. You guys familiar with the concept of a tuple? Somebody describe what a tuple is? Yeah.
It's basically just two items, like it's basically just a 2-item unit of data. You got one marker that keys into your header, and then the other one that actually has the data.
Well, so tuples don't necessarily, despite the name, can have more than 2 values in it, but it's really just an ordered set of values, right? The reason that we use tuples is to make it very clear, at least in this case, that we expect our records to have, all of our records to have the same number of columns, right? The same number of entries. I'm not going to have one row that's got 10 columns and another row in the same table that's got 11. That doesn't happen. They're all the same size in the same table. So you'll hear me use tuples and records independently of interchangeably with one another. That's what I'm referring to. Heap pages are typically constant in size. This makes sense, right? I'm trying to control how much stuff is in memory at any given point. So I don't want to have to worry about having pages that are larger or smaller than other pages. I'm just going to keep all my pages the same size, and now I know, exactly how many pages I can read in before memory is going to start to become a problem, right? This, though, has some other effects. Can anybody think of a possible detriment to keeping pages constant in size? Or maybe there's another question to ask. What happens if I get to the end and I want to put another record in, but there's not enough space for it? What am I going to do? We got 2 options, right? Yeah.
Does the whole file have to be like
An integer number of heap page? Yeah, well, I mean, a heap page is a unit, right? When I create a new heap page, it's all empty, but it's the same size even as a heap page that is full. They're all the same size. So if I get to the end of a heap page, I want to put another record in, I have a choice to make. I can split that record up and store it across 2 heap pages, right? We would call that a spanned record because it goes across multiple heap pages. Or I can say, I don't want to break this record up. I want to keep it as a single unit, so I'm just going to have to make a new heap page and put the entire record on that page. Of course, the cost of that is I've now got space at the end of my heap page that's not being used, right? So there's trade-offs. Again, it's always about the trade-offs that you are willing and able to make when it comes to implementing a system like this. Yes?
So when I finish reading the heap file, a whole heap file, but there's a space in the memory. So so as we know that for the memory I'm reading pages, okay, a specific number of pages. What if that file, so the final set of the pages from the heap file has we have extra memory. So can we read from another heap file?
Well, so I'm able to read in more than one page at a time. So if the question is, can I read in from multiple heap files at once? The answer is yes, absolutely, because I can have multiple pages in memory at once, right? I forget how many I have you use on the assignment. I want to say it's 32, maybe. I don't remember. 64, something like that. So I have enough memory on my computer anyway for 64 pages. Your computer maybe could do more or less depending on how much memory you have, but 64 pages can be held in memory, and those pages can come from any heap file. It does not matter to me where they actually come from. But I think it's important, and a lot of people struggle with this on the first homework assignment especially, to realize what each particular piece is responsible for in this process. The heap file, its job is to manage the heap pages. And that's really about it. The heap file's main task is to keep track of how many pages it has and where to access those pages. Maybe create new pages if it has to, right? Got to make some new pages when I run out of room. But that's really about it. The heap pages are the ones that are actually putting the records in, taking the records out. Right? So there's kind of a hierarchy there. Heap file manages the heap pages, which manage the tuples, which are really my records, my rows in my tables. Does that make sense? Any questions so far? Yes?
So does the heap file on disk contain a header for every heap page?
Actually, no. The heap page does not contain a header. It doesn't need to. Why not? It's a great question. The heap file actually does not need a header. The heap pages need headers to keep track of the records, but the file does not need a header to keep track of pages. Why not? Yeah. They're all the same size. They're all the same size. So if I go to a heap file and I say, how many pages you got? The heap file says, well, the file is this big, a page is this big, I must have this many pages. So there's no need for the file to store anything on disk in regards to the pages themselves. There is not an overall header, no. When I look at here, maybe it'd be helpful to draw a sketch of what a heap file actually looks like. Where'd my chalk go? If I'm looking at a heap file on disk, right? Here's my heap file. It's going to be broken up into equal sized chunks. So pretend these are all equal in size. Those are my heap pages. At the beginning of each heap page is a header. But be careful, this header is just for this page. It's not for the entire heap file. This page will have its own header. This page will have its own header. This page. So it's just a contiguous set of heap pages glued together. So if I'm a heap file, right? So a heap file really only exists then in code. I mean, it exists on disk as a collection, but a heap file in your code is going to say, oh, you want to access a tuple that's on page 3. All right, 0, 1, 2, 3. This is page 3. The file begins here. Page is X number of bytes long. Let me pull page 3 for you and give that back to you.
But they do have the headers that say.
I'm sorry? The headers are on every page, yeah. The headers are part of the page, for sure. So when I say a page is constant size, everything goes in that size, including the header. Yes. And these are on disk. Yes, the headers themselves are on disk. Yes?
How does the heap file know about the size of the pages?
The page size is constant. So
Where is it stored?
where is it stored? Well, we're going to decide up front. I want heap pages to be this size, and then we're just going to code it up as a constant. For our purposes, I want to say it's 4 kilobytes. But it's completely arbitrary, has no reason for being 4 kilobytes. You could change it if you wanted to. Yeah?
Can two different tables have different size heap pages, or is the page like consistent for our entire data?
Great question. Can two different tables have two different size heap pages? Theoretically, it'd be possible. In practice, I think that introduces some complications, right? It's better for us to keep all the heap pages the same size. Because then, and this is looking sort of way ahead in the future, I can have a pool of heap pages. And actually, this is homework assignment number 4 that we're talking about right now. You are going to have a pool of heap pages. The reasons for that will become a lot more clear when we talk about concurrency issues on databases in the future. But theoretically, sure. If you wanted to make them different sizes, you could. At the very least, I think you'd want them to be multiples of each other, right? This page size is twice as big as the other one, maybe. So it's somewhat consistent. Great questions. Any other questions? Any other questions? And so, while this system certainly does have its share of inefficiencies, especially in terms of space, potentially, in terms of performance, it's pretty good. The header helps us out a lot when locating stuff within the page, and then just the pages themselves help a lot in terms of performance by keeping things in manageable chunks. All right, what's next? Oh, exercises, great. So, excuse me, we have half an hour left. And for that last half an hour, I want to start on some exercises. Here's a nice little hint. All 3 of the exercises that I have are directly related to homework 1. In fact, some of these exercises, the answers to them are answers to issues that you're going to run into on the first homework assignment. So I love doing in-class work. I love doing in-class practice problems. So the way this typically works is I'll give you a few minutes to talk to your neighbors, work on them together as a group, right? You're not going to get graded on these, at least not right now. You'll get graded on the homework, of course. Talk about these. I want to do this one, but I'm going to come back to it. I want to do this one first. So you're given a heap page of size M and a record of size N. I want to know how many records can fit on the page. Here's a hint. It's not M divided by N. It is not. Take a few minutes, talk to your neighbors, see if you can figure out what the hell I'm talking about, and we'll go through the solution up here on the board in a little bit. Okay, this seems like a deceptively simple problem, but it's kind of not. And some of you might be thinking like, well, you didn't give us enough information to solve it, right? So I don't know how many of you maybe tried to introduce another factor in here, but there's a sort of a missing piece of information, which is size of the header, right? But I would argue that you know how big the header is going to be, kind of. How big should the header be? How big should the header be? And what? N is the size of a record, so that not quite. Not quite. So what's the header represent? The header is filled with ones and zeros where'd my chalk go? Header's filled with ones and zeros, right? Where a 0 represents that this particular slot is unoccupied, and a 1 represents that the slot is occupied. How many of these am I going to have? Yeah. One for each record in the file. Well, wait a second. That's what I'm asking you to figure out. Like, how are you supposed to... that's the trick, though. That's the trick. So the header is based on the number of tuples that I can fit in a page, which is what we're trying to figure out. So let's maybe come at this from a different angle. When I store a tuple in a page, how much space does it require? Might seem like another really dumb question, right? It says right there, n, but that's not right. N, yeah. N plus 1 bit. Plus 1 bit for the header. That's how much space it requires in this setup. So if we assume n is in bytes, m and n are in bytes, now we have a unit mismatch, right? N is in bytes, m is in bytes. Okay, I need to do this computation in terms of bits. I got to do this in terms of bits. All right, so that lets us get started. The amount of space that a tuple takes up is going to be n times 8 plus 1, where this bit represents the bit in the header, right? And so then if I want to know how many tuples can fit in the whole thing, I have to figure out how many bits are in the entire page, which is m times 8, then do my division. Does this make sense? I told you it wasn't m over n. It kind of is, but there's a little bit extra, right? We have to take that header into account. Question? Yes, if they were given to you in bits, you don't need this factor of 8 anymore. Yeah. Yeah, go ahead.
So the 1 is for the header. Is that just to indicate whether, like, for example, we have data stored in it?
Yes, that is what this bit is doing for us in the header.
It's like an on-off bit.
It's an on-off bit.
So it's not used for traversing between.
It can be, though. It can be. Because if I look at the header and I see a 0 here, then I'll just skip that particular. So maybe let me expand my diagram out a little bit, right, to hopefully illustrate this point. The first bit represents the first slot in my file. The second bit represents the second chunk of space in my file. We're dealing with fixed length records here, right? Or even if we weren't dealing with fixed length records, this would still be applicable. It would just take a little bit more math to make it work. But if we're dealing with fixed length records, this bit deals with this slot. This bit deals with the second slot. The next bit deals with the one that comes after that. So if I see a 0 here and I'm looking for something, I'm just going to skip this entire chunk and go to the next one, right? I see a 1 here. Okay, this slot is occupied. There's data there. I need to check it. Right? Does that answer your question? Yeah. Yes? What if the header is more than 1 bit? Why would it be more than 1 bit?
If the size is very large, then the header will need to record more information or data.
Oh, I mean, if we're using a different setup, right? Yeah, this all changes. But this is this is literally how your homework assignment is set up. With this header set up in this way. This is how your homework assignment is set up. So 1 bit, fixed length tuples. So 1 bit points to each slot in the page. What that means is, again, too, we're using fixed length tuples, and we still have that problem where I get to the end and I can't fit a tuple here anymore. So this is all wasted space. That still exists, but if you're using variable length tuples or you wanted to track more information here, like offsets or something like that, then yes, your header would take up more space. But this is the setup that we're going to be using in this class. It's going to have as many bits as there are records in the heap page. 1 bit per record. 1 bit per record in the heap page. If it'd make you feel better, make up some numbers, right? For our for homework assignment 1, our heap pages are 4 kilobytes large, and I'm going to give you some records that are, I think, 8 bytes. 2 columns that are both ints, 4-byte integers. So you can do the math and figure out how many of those would fit. It's not 4 kilobytes divided by 8 because there's 1 bit for every record. So that takes up a little extra space. For one table, this header is going to be one size, and for a different table, it's going to be a totally different size, depending on the sizes of the records that are being stored. So if I have a really long record, I'm not going to be able to fit as many of them into a page. This header is going to be shorter. If I have a really small record size, I'm going to be able to fit a whole bunch of them on a page, and this header is actually going to be larger to accommodate that fact. 1 bit per record in the page. Yes?
So even though we're using fixed size records, header's going to be bigger.
The header is not fixed. Yeah, the header is not fixed in size. That is correct. It is the same for every page in the same file, though. It just may not be the same from file to file. Yes?
So when you read it, how do you know that you hit the end of the header?
How do you know that you hit the end of the header? Well, I know the size of the page. I know the structure of the records contained within that page. I'm going to do this math right here, and that tells me exactly how many bits are in the header. This, quite literally, is going to be something that you plug into code on homework assignment number 1. Any other questions? Any other questions? Let's see. I'm starting to wonder if we'll have time to get to all 3 of these. So which one should I do? Let's do this one, actually. I think this might be the harder one of the 2 problems remaining, but that means it's a good one for us to talk about. Develop pseudocode for adding a record to a heap file. Now remember, a heap file is responsible for managing pages. The pages then are responsible for taking care of where the records go. So I said adding a record to a heap file. So I have a heap file, right? And I want to add a record to that heap file. What does that heap file need to do to put that record in the appropriate spot? There are easy cases, and then there are edge cases. The edge cases are where things get a little complicated. I want you to think about those edge cases a little bit. Take a few minutes, talk to your neighbors. This can be very loose, right? Maybe you don't even want to write pseudocode. You just want to write like step by step. Step 1, look at this. Step 2, look at this. That's fine. However is comfortable, most comfortable for you. But try to accommodate as many of those edge cases as you can. Yeah?
Are we saying we're appending them at the end or just sticking them?
Oh, okay. Well, we're using, so the question was, are we saying we're going to append them at the end, or are we going to stick them in the middle? We have this header for a reason, and that's to stick them, be able to stick them in the middle. So try and put them in the middle. Keep the space down.
Wonderful idea of like a heap
there's various implementations, and we're using an implementation that tries to reduce the waste of space that occurs from tacking it onto the end. Okay, we're running out of time. Let's see if we can come up with a solution to this real quick. I've got a heap file. Maybe it looks something like this heap file, and I want to add a new record to it. I want to add a new tuple to that heap file. So at a very general, high level, right? What's the first thing I need to do? Find a what? Yeah. I got to find a page, but I got to find a page that satisfies a particular condition, which is it has an empty spot. I have to find a page that has an empty spot in it. Some of the pages might be full. If we're getting good space utilization, which I hope we are, then a lot of them might be full, right? So I need to then loop through all the heap pages that I've got available. I know how many heap pages I have, right? Because they're all the same size. And so I just look at the size of the entire file divided by the size of a heap page. That tells me how many pages I have, right? So if we're doing pseudocode, we'd say, you know, for each page in file, we're going to ask that page, hey, do you have an open slot? Do you have space available? Right? And if it does, then we're basically done. We give the tuple to that page and say, here you go. Find a place for this. So if page has open slot, add tuple to page. There's one very important edge case here, though, which is, yeah.
You don't have an open slot, but the page isn't full yet.
Don't have an open slot, but the page isn't full yet? What would, I'm not sure.
The header, you just add more there. Like, what if you may have like 4 slots in there or something like that that are all full, but you could add another record into there. But you have to add another bit.
Well, the header, no, the headers, let me make this clear. If I have a brand new heap page with nothing in it, the header is going to be already there, and it's going to be all zeros, right? And as I add things to it, I'm just going to change these to ones, but it's not going to change the size of the header. It's just going to change the zeros to ones and vice versa. It's fixed within the header size is fixed within a heap file, but if I look at this heap file and another heap file, they might have different header sizes because the size of the records that I'm storing are going to be different, right? I'm sorry? Oh, because I just randomly picked one? No, I mean, no, I was in a hurry and I erased the first 0 with my hand, right? That's all. Don't read too much into it. What's the edge case? What's the problem? Yeah. All the pages are full. So we got to add a new page, right? So I need to have some way of knowing whether this worked or not. If I get through this loop and I don't find any pages that have extra space, down here, right? Create new page. Add the tuple to the page. So this is the case if everything is full after this loop. If we go through this loop, we don't find it, then we got to add a new page. Surprisingly, or maybe not surprisingly, a lot of people forget this part. I'm going to be checking for that on the assignment. Definitely, definitely, definitely. Any questions? There's one more exercise that I skipped over. We ran out of time to get to it. It has to do with tuples. I feel like it's relatively straightforward, but also directly related to the homework assignment. So if you want to think about it, you can. If you want to ask questions about it, I'd be happy to talk to you about it. Otherwise, on Tuesday, we're going to talk about the first homework assignment. I'm going to show you some code. You're going to write some code. It'll be a lot of fun. Have a great weekend.